Okay, here we are in week 9, COMP7010. This is the Equiv chapter, and what we're interested in this chapter is extending our thinking about the imp language to program equivalence. So basically, if we've got two programs or two fragments of programs, what do we regard as equivalence between those two programs? So this is useful for things like if we're doing an optimization in a compiler and we want to transform a program into a better version of that program, we'd like to be sure that we don't change the behavior of the program when we do that. So we'd like to know, for example, that the optimized version of the code always behaves the same way as the unoptimized version of the code, for some definition of behaves the same way. So that's what the equivalence thing is that we're going to talk about here is, and there are different ways to do this obviously, and we're going to just do it for the imp language. The details will vary obviously for different programming languages. Okay, so we'll start off by talking about what equivalence might mean. So it's this behavioral equivalence. So you can think of it informally as if I run a program or an expression or something, the same thing happens, okay, for two different expressions. So the definitions for expressions are pretty straightforward because the semantics, in other words, the meaning of an expression in our language here is that you just pick the state that you were interested in and then you evaluate the expression in that state, and you get a number for an arithmetic expression and you get a Boolean value for a Boolean expression, and we say that the two expressions we're comparing are equivalent if we get the same answer for every possible such evaluation. So here, for example, in aequiv, we're defining this to be a property that says for all states, so we're considering every possible state that could happen, then it must be the case that evaluating one of the expressions in that state gives the same answer as evaluating the other one. Okay, and this is a pretty tight constraint, right? So this is a bit like writing lots of tests that's, evaluate the two expressions in the same state and compare the answers each time, but it's stronger than that because it's quantified over every possible state that we can have, not just some states that we happen to come up with in our test suite. Okay, so the same holds for Boolean expressions. So bequiv is exactly the same thing, except it's using the Boolean evaluation, and so what it's going to be comparing here is Boolean values instead of natural numbers, but the idea is the same. Okay, so for commands it's a little bit trickier because we have this notion that some commands might not actually terminate. So we need to somehow factor in the termination of a command into the notion of equivalence. So we would probably want, for example, that if one of the commands terminates when run in a particular state and the other one doesn't, we would want them to be regarded as not equivalent. Okay, and in some sense you could say if a statement or a command always doesn't terminate, then it would only be equivalent to other things that never terminate as well. Okay, so the definition of the equivalence for commands is a little bit more subtle because it has to basically say something about the termination of this thing, whereas in the expression cases they always terminate, right? There's no possibility for an expression to just keep running forever. So CEquiv here is the analogous equivalence proposition for these, and it basically says that if you run C1 starting in ST, some state, and it ends up in some other state ST prime, then it must be the case that if you run C2 in ST, you also end up in ST prime. And both directions have to hold. So this is an if and only if constraint. Okay. Now it's important to think about what this means. So it's not going to be quantified really over every state, because only some of the states are such that if you run the command in that state, it will terminate in some other state. Okay, there may be some states where if you start the command in that state, it never terminates, and that's not covered by this definition, because this relation, this is a three-part relation. This relation is only talking about terminating evaluations. Okay, so for example, if C1 never terminates, doesn't matter what state you start in, then this highlighted piece can never hold. Okay, and then we would require the other side to never hold as well. So C2 should never terminate in any starting state. And then we can say they're equivalent sort of vacuously, because there are no states ST and ST prime where this holds. Okay, so so there are no such states, so it holds for every possible state that this is true for. Okay, so that's the difference. Is the equivalence of things that are always terminating is easy, because you just run them and see what the answer is, and the answer has to be the same in all cases. For things that might not terminate, we need to, well, in this definition of equivalence, we're only considering the evaluations that terminate, and those must terminate in the same final state. Okay, so that's the sort of high-level view of it. We're going to use these definitions a little bit later. The next part is just pencil and paper exercise to get you thinking about equivalence. So the idea is that there's a bunch of programs here, 7 or 8 or something, no, 9 I think, and what you've got to do is look at the programs and try and determine which ones are equivalent with which other ones, using that definition of command equivalence that we've just defined. Okay, so what I would encourage you to do is to sort of pause the video here and have a look at these programs, have a look at them all, and try and partition them into equivalence classes of programs that are equivalent to each other. And then once you've had a go at that, come back and I'll go through my version of it next.